Hello friends, this is quantum mechanics question paper solution part 5 of 5th SEM physics honors students. This is paper of 2021 set by Dibrugarh University. Dibrugarh University. And this is paper C-11. Okay, and this is part 5. In the last video we have solved up to question number 10, right? So in this video we're gonna start from question number 11, right? So link of the last video, part 4, is given in the description box. If you haven't watched the previous parts from part 1 to part 4, all the links are given in the description box. If you want to watch, you may go through them. So let's start. Before we start, please subscribe the channel if you are new to my channel, and also share with your friends if you think my videos are helpful, and also hit the bell icon so that you get notified when new video will be uploaded. Okay, so now let's start. So this is question number 11. Describe the Stern-Gerlach experiment for the verification of space quantization. Okay, so before you write the answer, let me explain about this experiment. Okay, so in this experiment, a beam of silver atoms is being, it is allowed to pass through a inhomogeneous magnetic field. So this is suppose these are the two poles of a magnet. This is north pole and south pole. These are the two poles of a magnet, and a beam of silver atoms are allowed to pass through this. And now you see the view of these two poles from this side. If you see the poles from this side, edges seems to be like this. So these are the edge of the poles, something like this. Okay, and the magnetic field lines are something like this. Okay, this is not homogeneous, it is inhomogeneous magnetic field, right? And if you take this as a so here, let me take the detector here, this detector plate that will detect the atoms. So when this magnetic field is turned on, then here we will get deflected atoms, okay, into two groups, right? So why does it happen? So let me explain. Now silver atom has 47 electrons. So these are the electrons of a silver atom. So now you see a neutral atom, when it is passed through this magnetic field, it should not get deflected. It should strike here, right? So now you see in silver atoms, if you see this electrons, now you see I am using here two different colors to represent spin up and spin down, right? And here you see in this orbital, so you have one unpaired electron. Okay, so in case of paired electrons, the spin up and spin down, they are cancelled by each other. So that's why, so here, because of this unpaired electron, its spin its spin may be up or may be down. Okay, both cases possible. So when such atom, when this one sodium atom pass through this magnetic field, so the direction of the spin will rearrange either in the direction of magnetic field, or in the opposite direction of the magnetic field, depending on the orientation of the spin before it enters the magnetic field, right? So depending on orientation, up or down, along the magnetic field or in the opposite direction of magnetic field, it will be deflected in upward direction, in downward direction. So this experiment shows that the existence of electron spin. That means the space quantization is verified. So let me tell you how to write the answer. Here you can see, let me go to the previous slide. So this is the diagram, experimental setup. So I have taken this direction as y direction, as you can see here, and these are the two slits, slits for obtaining a narrow beam silver atoms and strong poles of magnet. And here is the detecting plate, where the atoms will be deflected, where the atoms will be striking after deflection. So, and these are the magnetic poles, and these are the cross section of magnetic poles as I have shown here. And here the electric oven that vaporize the silver atoms and fire the atoms, silver atoms. Okay, so now this method that I have already explained, and this is the explanation that I have already done. So you can pause the video, you can write it. Now let's go to the mathematical part. For the angular momentum, quantum momentum, L is equal to 0. So magnetic dipole moment, this one mu L, that's gonna be equal to 0. Okay, so because the silver atom has outermost electron in this orbital 2s half state, right? 2s half state. So here you see this quantum number L must be 0, and if that is the case, then this electron, the magnetic dipole moment mu L of the electron is 0, hence the electron has only spin magnetic dipole moment, right? Now field of flux density, we have considered the magnetic field that we have applied, that is B, and the additional energy of the atom is given by this E is equal to minus mu s B cos theta. So here theta is the angle between mu s and B, right? And we have taken this as equation number 1. Here you see this is equation number 1, and this is the cos component of mu s and in the direction of magnetic field. So this component, it has two quantized value. This is the value here, positive E h cut by twice m or negative E h cut by twice m. Okay, and that's gonna give you, if you use this value here in equation number 1, then you're gonna get this value, right? This is equation number 2, and if you differentiate this, then you're gonna get this force Fz acting on the atom along z axis, right? Determine the if you determine the differentiation, you will get this result. This is equation number 3. Now you see, let's go back to the diagram. So that means this is, you say this is the direction y-axis, and the atoms are moving in this along y-axis, and the Fz is the force acting in this direction, in z direction, right? So now let's go back to the equation again. So this equation 3 gives the force along z direction. Now let's go to next slide. Now acceleration A in z direction, that will be given by Fz by m by this formula. That means we know that F is equal to ma, right? F is equal to ma, so A must be given by F by m. So as we are going to find along z direction, that's why we have to take Fz here. So now, and putting the value that we have already obtained, putting the value of Fz we have already obtained in this slide here, you see in equation number 3. Here if you put this value of Fz, then you will get this result. This is equation number 4, right? So now let t be the time taken to travel through the field, and here this capital L is the length of the path, right? This length of the path through the field, this length is L, suppose. Okay, that then this t is given by t is equal to L by v. V is the velocity, right? The displacement d of atom in z direction emerging from the field is given by, that means suppose this is the detecting plate, right, which detect the strikes of atoms, and from this position where the atoms should strike in absence of magnetic field, this is the position suppose, and in presence of magnetic field the atoms strike at this position, right? And this distance is d, right? So that's it, and that will be given by d is equal to half at square, So that means you can use this value s is equal to ut plus half a t square, where u represents initial velocity which is 0, right? We are using those kind of concept here, so that's why half a t square is will give you this distance d, right? So now you see, if you use the value of a, this value of a from equation number 4, then you will get this result. And if you also value of if you use the value of t, that L by V here, right? So using those values, we have got d is equal to this, right? And assuming that the distribution of speed among the atoms in the source is given by Maxwell-Boltzmann speed distribution law, that is this, that is equation number 6, right? So k is the Boltzmann constant, T is the absolute temperature, right? And if you assume that also we have taken small m is the mass of silver atom, and assume that V is equal to Vp, right? So in that case, this equation number 5 gives you this equation, and at the end we're gonna get this result, that is equation number 7. And this expression gives the theoretical value of d, that is found to be agreement with the measured experimental value, right? So this experiment shows that thus the postulate of space quantization and existence of spin electron is verified, right? So this is the answer of question number 11. So hope you have understood. Now let's go to question number 12. So now question number 12. So what is normal Zeeman effect, right? So let me write the definition first. So here is the definition: normal Zeeman effect. So normal Zeeman effect is the splitting of spectral lines of an atomic spectrum due to the interaction between the external magnetic field and the orbital magnetic moment. So this is the definition of normal Zeeman effect. Now, on the basis of quantum theory, explain the effect of magnetic field on energy level of an atom. So here is the explanation. Now let us consider an atom having orbital angular momentum. So L, this L vector represents angular or orbital momentum placed in an external magnetic field. This is B, right, along z axis, and its quantum state be specified by the orbital quantum number, that is small l, and the energy is E. Okay, the interaction energy del E of the atom due to interaction between the magnetic moment and the field is given by del E is equal to, so let me write here, let me write the expression here. Del E is equal to minus mu L, which is the magnetic dipole moment, right, dot B vector, that's equal to minus mu naught L B cos theta, mu naught L B cos theta, right? And you see here, this theta is the angle between, this is the angle between this angular momentum and vector B, right? And now you see, we know the value of mu L is given by this expression. Let me write clearly. So mu L, that is equal to minus E by twice m into L vector, and cos theta is given by cos theta is equal to, that is Lz, that is the z component of L, by L is equal to, which is equal to ml h cut by capital L. Now let us use these two values here in this first equation. Okay, in this equation, then you're gonna get this value, that del E is equal to E h cut by twice m BML, and this value, this is nothing but mu B, this is Bohr magneton. Okay, when mu B is equal to, so you can replace this EH cut by twice m by mu B. So let me write here, E is equal to mu B, that is EH cut by mu B BML, right? You can replace the expression for energy, interaction energy, by this expression, so, right? So hope you can recognize this writing. Okay, I have taken the photo directly from the book. Just now let's go to next slide. So here you see, thus the energy of energy of the state E is given by E is equal to E naught plus mu B, right? Mu B into capital B M L, right? So E is given by, so let me write here, E naught plus mu B B M L, right? And this part is the interaction energy. So but this m small ml has twice L plus 1 values, okay, and those are minus L plus 1, then dot 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 0, then L minus 1, then L, right? And so the energy can have L plus 1 values is slightly different and determined by ml, right? This is ml, right? But every line splits into 3, right? Every line splits into 3 as the transition between the states of different L values is controlled by so-called selection rule. These are the selection rules. Del L, that is given by plus minus 1, and del M L is equal to 0 comma plus minus 1, right? So now consider the transition between initial and final energy levels. EI is the initial and EF is the final energy level. So EI, initial energy level, that can be given by E naught I plus mu B into B MLI, right? And the final one is given by EF is equal to E naught F plus mu B into capital B M small L F. This is the final, and subtract these two, the E initial, E final, then you're gonna get this result, E naught I minus E naught F plus if you subtract these two, then you will get mu B minus del ml. So here this del ml is nothing but the difference between mli minus mlf, right? So that is del ml. So hope you have understood this. So in this ei minus ef, that is equal to h nu, right? So we have used that relation here, h nu, and E naught will be h nu naught and plus mu B into B del ml. So, and this implies this equation, mu is equal to mu naught plus EB by 4 pi m del ml, right? Now let me explain these things with the help of examples. Suppose this is an atom, nucleus of an atom, and an electron is revolving around it, right? This is the orbit of the electron, and here is the this this is the angular momentum, and here, and this in this opposite direction we have magnetic moment, and these are opposite in direction. That's why you see in this equation we have used minus sign here, so in relation between this L and mu L, right? So hope you have understood this, and we have applied the magnetic field in this direction, so along z axis, right? that is what we have done, and the z component of L is this LZ, right? So now you see here this ml is nothing but magnetic quantum number, right? So now let's go to the next slide. Now let me show you the transition between these two states, L1 and L0. This is the L0 and this is the L1. So for L0 we have got that ML has twice L plus 1 values. So for L is equal to 0, this ML will have 2 into 0 plus 1, that will be 1. So there will be one value, right? If there is one value of ML, then that will be 0. Okay, that will be 0, right? So now if you take L is equal to 1, then ML will have 2 into 1 plus 1, that means 3 values. And if it has 3 values, then those will be 1, 0, minus 1, right? 1, 0, minus 1, because we have already got that values of ML are given by minus L plus 1 dot 0, then again dot L, then L minus 1, then L minus 1 comma L, right? So that's the logic here. So that is what we have applied. So we have got L is equal to 1. So as we are taking L is equal to 1, then ML should have minus L, that is here minus 1, then minus 1 plus 0, that means 0 here, then here you see, then L, this is the L here, right? So hope you have understood this. So if you take L is equal to 2, then it should have 2 to the 4 plus 1, 5 values. Then so ML will have 5 values. Those will be as we have taken L is equal to 2, then those will be minus 2, then minus 1, then 0, then 1, then 2, right? So if you take L is equal to 3, then you will have minus 3, minus 2, minus 1, then 0, then 1, 2, and 3, so on. That's how we do, right? Now you see here this is for L is equal to 1. So here we have got the values of ML. This is plus 1, this is 0, this is minus 1. So we have got 3 states, and here for L is equal to 0, we have got value of ML, one value of ML, that is 0, right? And these are the transition as I have shown here in this figure, right? For ML is equal to 0, so V1 is equal to V0, right? For ML is equal to 1, V2 will be equal to V0 plus EB by 4 pi m, right? So because we have got this experiment in that mu is equal to mu naught plus EB by 4 pi m and del ml. So if you put the values of del ml here, 0, 1 and minus 1, you will get these 3 levels, right? Okay, that is demonstrated here. So hope you have understood this. This is the answer. So you can pause the video and you can note it down, and remaining questions will be solved in the next video. So thank you for watching. See you in the next video. And before I say goodbye, just subscribe the channel if you are new to my channel. Also share with your friends and inspire me to create new videos, and also help me to grow my channel. And also hit the bell icon so that you get notified when new video will be uploaded. So thank you.